Okay, so welcome everybody to this only talk of the afternoon session. And we have Chris D-Orr. He'll talk about some new cases of Zilber-Pink in Y1.
So thanks very much, Gal. Thanks to Jacob, thanks to all the other organisers for both the conference and for the special year. I'm only here till the end of October, but I'm having a great time. So thank you very much. Right, so yeah, I think my lecture's going to be a change of pace a little bit. Yeah, the main topic is the Zilber-Pink conjecture, and so people have pointed to it and said some things about it. But just to put what I'm saying in context, let me just put it on the board. So this is a conjecture, of course. And we've seen that you can make this conjecture in lots of different settings, but for simplicity and because of my own limitations, let me just do it for Shimura varieties. So the statement is as follows: you fix as your ambient space a Shimura variety, and then you take a irreducible subvariety, and you choose this to be, we sometimes say Hodge generic, so this came up earlier. So you just don't want V to be in some smaller Shimura variety. And then you play the unlikely intersections game. So you take V and you intersect it with the Shimura or special subvarieties that it shouldn't intersect, just for dimension reasons. So you look over the union of these. There's not a lot of space here, but so that should be a special or a Shimura subvariety whose codimension is exceeding the dimension of V. So just based on this, you expect each one of these to be empty. You're varying over a countable collection of subvarieties. This union is expected to be small. This is a Zariski game that you're playing. So the expectation is, okay, let me say then. So this is if and this is then. This is not Zariski dense. In V. So my feeling, hopefully it's not contentious, is that geometrically, or the geometry of this problem, which is a very vague term, but yeah, so I mean, Greg explained in some detail. Roughly what I mean is when you look at the intersections here that have positive dimension, this is well understood, I would say. For the point of this problem, maybe entirely understood. And okay, not to put too fine a point on it, but that's basically because of these staggering developments over the last few years around things like functional transcendence, homonormality, etc. Right? And the whole workshop, the whole year is, at least to some extent, devoted to all of these amazing things. But on the other hand, this is the message of my talk, is that the arithmetic. So again, just to be a bit vague, the intersections that are just points I would argue that these are poorly understood in general. Except, let's say, maybe with a few sort of striking exceptions, except when those intersections are, say, CM points, And then you get something along the lines of what's called the André-Oort conjecture. Okay, and that was recently resolved. I mean, there's a whole list of works. It's kind of an incredible story. But the most two recent papers, the first by Galbin-Yamini and Harry Schmidt and Andrei Yefayev, which is sort of some kind of counting strategy, and then a paper by Anand Shankar, Zilber-Pila, Jacob Zimmerman, and the appendix by Helene Ngo and Michael Gurchinek, which put together the last sort of arithmetic parts of this problem. So that's a very notable exception. There's also the sort of arithmetic problem when you just look at points all lying along one Hecker orbit. And that has some sort of close connection to what's called the André-Pink-Zanier conjecture. And that was also resolved at least for small varieties of abelian type by Rodolphe Richard and Andrei Yefayev. So those are very notable exceptions, but they are nonetheless very, very particular points, right? And the points showing up here could be, you know, very, very general. And the arithmetic of those, I would say, is a very wide open problem. So let me try and make that point more explicitly. So what's the okay, so if you don't care about small varieties, that's fine, because now they're gone, you can forget about them, except in this very special case. So what's the simplest Chamorro variety? Well, it's just Y1, right? Which is a variety, it's just the F1, right? Now, okay, this on its own isn't going to do for unlikely intersections, so I have to make it a bit bigger. But I can make it big enough by just taking threefold Cartesian power. And then I have enough dimensions to do unlikely intersections, so I can work with a curve. Let V be dimension 1. And then, yeah, for things to be unlikely, I need to intersect with Z's. Have dimension at most 1. So, apologies, because I know some of you know this sort of ridiculously too well, but let me just remind you, what are the special stubs in this situation? Because of course, in general, like if you want to talk about what are the special subvarieties, some variation of constructors, you might have some non-trivial task, but here, like the classification is incredibly simple. You just take the irreducible components of finite conjunctions of two sorts of relations. All you can say is that one of the coordinates is a CM point. As you did, sorry, that's not very precise, is it? I mean, like fixed to be one specific CM point. Yeah, maybe it's or two of the coordinates are satisfying one of these modular polynomials, which, you know, from a modular interpretation just says that the corresponding elliptic curves have a cyclic isosceles degree. That's all you can do. So I just want to quickly review what we actually know about Zilber-Pink in this kind of ridiculously simple situation. Okay, so as I said, if you just look at specials of dimension 0, then that's the André-Oort conjecture. And so, okay. The André-Oort conjecture in y1 to the n is due to Jonathan Pila. Of course, for y1 squared, it was also proved by André. And as I'm dealing with the curve, I did wonder if maybe one could extract prove that. So I'm not quite sure, but I put those two names. So this is okay. Also is okay, a bit later, is if you just look at z's that have a fixed coordinate. Right, so as long as you have one of these conditions in the definition, then everything works out. And that came later in a paper of Habegger-Pila. And then okay, these are sort of relatively arithmetic problems. Just to add another thing into the geometric mix, because of course there's not really too much geometric in sort of the sense I was talking about here, but if V is not defined over Q bar, then also the problem sort of well, I don't want to be, becomes a geometric problem rather than an arithmetic. And that was also done by Pila in this case, but it's also true to say that for the general Zilber-Pink conjecture, for those kind of varieties where there's some kind of not over Q bar condition, we know a lot, and the most recent work is due to Klingler and Tiden.
Do they cover the case where S is a product? I thought there was
S is a... Oh, no, the condition is not like just not over Q bar, right? Like you have to go down to each simple factor and it has to be not over Q bar there. Is that about right? Yeah. So, yeah, not exactly as stated. So those are all good. There's one more result in the literature that I want to bring up. This is kind of the thing that has fascinated me for a while. Habegger and Pila also show that Zilber-Pink is okay if V is asymmetric. This is HP again. So this is kind of a strange condition. So their work is actually in Y1 to the n. This condition in Y1 cubed has a very simple formulation. So this is a subvariety of Y1 cubed. So you have these like projections down to Y1. And the condition of being asymmetric is just that the degrees of those maps are not all the same. Oh, I don't know. But somehow it's like, it's a bit like this one. It just makes the arithmetic work. Like here you have a CM point, so that kind of, it has some obvious arithmetic input. And so here there's some sort of ingenious argument based on, here you attribute it to sort of Siegel and D-Orr, right? I think. Yeah, it's kind of cool. But the problem is, this is difficult to remove, as far as I can tell. Difficult to remove. And also difficult to generalize because, I mean, this is in a Chaumont variety, in a product of one-dimensional Chaumont varieties, and very much written in the language of having hypotheses. So, yeah, somehow you need to, I think, come up with some new things. So we have some new things, and to formulate them, we have to talk about the boundary of our Chaumont variety. So, okay, in this case, the things are not quite as complicated as some of the other talks, right? So we have Y1 cubed. Okay, there are several ways to compactify it, but the Bailey-Rowe compactification is just P1 cubed. This is somehow the one. Okay, it's right. And then, well, what does the boundary look like? It's just 3 copies of Y1 squared. 3 copies of Y1. Yeah, 3 copies of Y1. And 1 more point. And so if you'll let me carry on my list, I had some bullet points. So by bullet points, I mean carrying on my list of cases of Zilber-Pink. Martin and I, so all of this is to come is all due with, all joint with Martin Orr and George Papas. Martin and I showed that ZP is okay if the Zariski closure of V contains this point, infinity, by which I mean, of course, infinity. George then noticed that actually you can do better than that. You're okay if the boundary of V contains a CM point, right? For now, you see, this is a fact for for all Chaumont varieties. The boundary components are themselves Chaumont varieties, and makes sense to say that there's a CM, you're hitting a CM point in one of these things. And Right, so that's where we were, and then we, as George said the other day, we teamed up, and we realized that we could extend this a bit further in the setting of, well, what happens if we intersect something else special in the boundary? So just to clean that statement up a little bit, let me I guess I decided to only use half the boards. I'll try to correct that in a minute. So just to clean that up, I'll say point in the boundary is boundary modular Bn. If x belongs to the vanishing locus of a modular polynomial, which makes sense in one of the y1 squares. So, in other words, I've gone to a point, I'm a point that sits on a modular curve in one of these three copies of y1 squared. And then the theorem joint with Martin and George is that ZP holds, Zilber-Pink holds in y1 cubed if the boundary of V contains a BM. So one remark, of course, aesthetically it'd be nice to be able to say something to the effect of Zilber-Pink holds if you hit, say, like a special curve in the boundary. But of course, that would include things that look like the fiber over a CM point, you know, a line attached to a CM point. But then, of course, you have somehow no control over what's going on with the second point, and this really is a fundamental blockage to what I'm going to explain. Anyway, so this was kind of a byproduct of our initial plans, which essentially was to try and do what I'll explain in a bit, which was sometimes we call the G function method for these unlikely intersections, which we wanted to try and do the G function method sort of in the interior of the Shimura variety. So this does lead, the sort of the full strength of our methods leads to something along those lines. But I have to make some definitions to define it. So first of all, note that by this classification and this history of the Zilber-Pink conjecture, we only need to prove finiteness of points on V, x1, x2, x3, that sit sort of on two modular polynomials, if you like. So such that there exists an m and an n, such that phi n x1, x2 was phi n x2, x3. Right, all the other kind of unlike intersections are dealt with. We only care about these ones. And so I give them a name to help speed things up. So these will be called modular points. I'm not wedded to this name because I know, of course, the word modular gets used a lot anyway, but just this is just for the purposes of the talk. And again, we're going to have to do some counting at some point. So I'll attach a complexity to this x. So I'll say delta x is just the maximum of m and n. And I think, yeah, if you were keen-eyed, you might protest that, well, if this was, say, had CM coordinates, maybe m and n are not uniquely defined, but I don't care about those kind of points because Andreor takes care of them. So for non-CM, this is a new uniquely defined quantity. And carry on with that. So the next theorem is about finiteness of modular points but with an additional property, namely they have few places of supersingular reduction. So this is a little clumsy. No, and so this is the key starting point for me. So know that you can always assume that you have some sort of base point B. That's modular. Okay, if there's no such point, then you're finished. So fix that and let K naught be its field of definition. And then I want to make a couple of definitions. So first of all, for any finite extension K of K naught, V is, sorry, a place V of that extension, finite place, is supersingular if the elliptic curve with J invariant B1 or equivalently B2 and B3 because of the isogeny has supersingular reduction of V. Okay, so I'm just saying, as if I don't care if I make some finite extension, but I'm sort of looking at the places where this fixed elliptic curve corresponding to this guy has supersingular reduction. Let me try and improve things now. So now, this is the clumsy part. I'm going to say that a modular point x1, x2, x3, let's call it x, on V, has supersingular exponent. Delta if the collection of supersingular places for which this point is v-adically close to the base point. So that is to say, xi minus bi is less than 1, is at most delta x to the delta. Right, so it's ugly, but it's a subset of the modular points that have, in some sense, a small number of supersingular primes. That are close, this will come up, this will sort of become a little clearer later on, that are close to the fixed base point that I can always take to exist. It's not a nice, not a natural, nice definition, but it's what we have.
So you fix the point B1, B3, then you take another point X1, X2, X3.
Yeah, so somehow B is going to be fixed at the beginning of the game, but then these x's will be the ones I try to constrain. Okay, so let me just do the theorem. So the second theorem says, so with Martin and George, there exists a delta greater than 0 such that V contains only finitely many modular points. Supersingular experiment.
About your definition.
Yeah.
That seems to be, that's like counting the number of primes.
Yeah.
I looked over there and I really either.
I don't mean to make, I'm not making any claim about the number of primes that points may have. I'm just saying I can just look at these, the ones that have this many.
And X doesn't have to be defined over K naught. X could be defined over whatever X.
Exactly. X is defined over what it is, something in Q bar, and then I take that, the smallest field of definition. So I just want to highlight one thing, because this is very much there's a theory. So I should say the method I'm about to explain was originally invented by Yves André, and even this theorem too, I feel is somehow very much in spirit to one of his theorems. He has a paper, Theorie de motif. And the theorem one in that paper is very much somehow an inspiration for this, and of course the proof is hugely inspired by what he's done.
So because to again go back to definition.
Sure.
Can I think of it as there's some place in the field of definition of X sitting above V where that happens?
What do you mean? So what is V? Sorry.
V is, so you have a place V of, oh, sorry, K naught of X, sorry.
Yeah,
V not-
V I think of as, yeah, because I want to take distance in a field.
So,
Yeah.
so in definition, you mean supersingular exponent means the very few supersingular points. Supersingular.
Yes, exactly. Yeah, somehow the supersingular primes, if you like, are going to be problematic, and I have to somehow constrain the number or only deal with points where that number is small.
It should be very rare to have supersingular.
It is that's right. It is very rare. I mean, of course, this set here is infinite. This is what makes it a finite collection. So
It's very rare, so we should expect it to be less than delta x to the power of delta.
yeah, I can't say anything intelligent about that.
If we expect it to be less than this exponent, then most of them should be infinite. Then most of the points should be.
Yeah,
enough.
I would like to say that this is a half decent theorem. But I don't think I can make any claim that this is somehow good enough or, yeah. But yeah, I do also feel slightly unsure about what is actually the full strength. There's more to be understood. Right, so let me say something very,
Excuse me.
sorry, yes.
So existence of an exponent, even without the modular condition, that is the consequence of the cross-Zagier factorization.
Okay,
Just the existence.
is George here or is he? Yeah, what, did you hear the question?
Here's the question.
The question was, is the existence of delta, what without,
With X2 and X3.
yeah, does it follow from Gross-Zagier heuristics?
Not heuristic,
Sorry.
factorization.
The factorization theorem?
That's for CM stuff, right? Like the cross-Zagier is for CM stuff. So here we don't have CM.
Yes.
Okay.
Yeah, I think, yeah, we did talk about this.
And even in the CM case, it doesn't follow.
Right, okay, well, that's good to know. Anyway, let me plow on, but I'm very interested to hear from experts about this whole thing. This is where the blockade is. Right, let me just say something sweeping. So there's a very powerful strategy for unlikely intersections called the Pila strategy, which is sort of behind most of the modern developments. And if you add that to isogeny estimates, sort of the form of Massey-Wustholz or sort of more effective versions, we use a version of Gaudron and Raymond. It's all that you're, in quotes, all that you're left to do is prove a height bound of the following form. You need a constant C such that the logarithmic ray height of X is growing something like field of definition to the C. There's of course an implied constant here, and in fact you can be even cheaper than that. You can have some sort of small, let's in quotes, small factors here. So I'm going to put a delta X to, let's say, the 1/2 minus epsilon. But for psychology, the meat here is, don't worry too much about this. The idea is that you want logarithmic height growing by some smaller than some positive power of the Gauss orbit or the field of definition. That's somehow the key ingredient that one needs. And that's nice because this is exactly the kind of height bound that André proved in his manuscript, G functions geometry, and that's therefore the direction that we've gone in. Right, so what a numbering. Okay, so let me start again now. So this kind of bound, sort of the logarithmic height of, say, a light intersection is bounded in terms of the Gauss orbits, is somehow the name of the game. And there's a strategy to prove this sort of thing, as I mentioned. So this is what I call the G function method, due to André. And it's often done, and it's sort of loosely speaking, around a point of degeneration. But now, and this was one of the main sort of motivations for giving this all a go, this is now the G function method in the interior. Because somehow with Zilber-Pink, the only thing you can be sure of is that you have one of these kind of cube points in the interior. And so somehow the natural thing to try is to try and do the, of course, I haven't explained the method yet, but to do the method around that point rather than some, hypothetical point of degeneration. So let me explain this in a very simple way. There's much more complicated generalizations, both in André's book and David Urbanik's recent paper. So consider an abelian scheme. It has to be over a curve and over a number field K. Let's say the relative dimension is G. And let there be some point S0, K rational on C. Okay, so we've seen all these gadgets a lot now. So of course there's the Dram cohomology, this family, and it has this flat connection, the Gauss-Manning connection. Let me call this sheaf W. So we may as well assume W is a free sheaf because removing finitely many points from C isn't going to lose us the game. So we'll choose a basis. That's an algebraic thing. And then we choose a place of the field, any place. So V in the places of A. And make a small open subset of the analytification of the curve. Contains the point S0. And then we choose a basis, another basis. But now in the analytification of W, restricted to U, but horizontal for the.
Do we have U before?
Sorry, U is, sorry. We did, but we called it W. Right, thank you. And so then, I know, apologies, this is it's very trivial to people. We take this matrix, which is just the omega I with respect to. And of course, so if we want, we could choose, in fact, if these gamma j's are somehow chosen a bit more algebraically, if you like, so in the sort of in the Q-bar local system underlying the Dram cohomology, so if they're in here, then we would call these the entries of that matrix the periods of the family. I suppose this would be if V was an infinite place. Okay, so that's a nice matrix and has nice geometric meaning. But to use it, we then have to sort of renormalize it by taking the inverse of its value at S0 and multiplying on the right by that thing. So now we get a matrix whose entries at S0 are just the identity. And then we take the Taylor series of Yij with respect to some local parameter. That local parameter x, because everyone phrase x again. Okay.
The effect of this omega S0 inverse is just to choose the gamma i's to the same position.
Yeah. So yeah, this is like cheating or because somehow the periods of S0 are something horrible and I somehow got rid of them. So I've kind of obfuscated the periods. But in so doing, these Yijs or the Fijs, so of course they're power series, but they're a special kind of power series. They're called G functions. So in particular, these power series now have coefficients in K. These are all Andre's observations. Moreover, not only do they have coefficients in K, there are sort of growth conditions. There are growth conditions on the height, growth conditions on the height of the coefficients. And of course, just so I've completed the definition, they satisfy a linear homogeneous differential equation. So, okay. And moreover, sort of suggested by this, I suppose, these are independent of the place I showed in the beginning. So, okay, so what? The point is that there's this kind of magical theorem in, I don't know, transcendence theory, it's the right word, I don't know if it was Eve that named it this, but I've been referring to it as because this is what is stated in this book. So they have a G function satisfy a Hasse principle. Yeah, sorry. Yes, of course, this is very important. What I wanted to ask you, and I never did, was did you term it a Hasse principle, or was that your? Yes. So let me write this down. Well, this is a general fact about G functions. So is the Hasse principle due to von Bieri, and he's being modest. He made some improvements. So what does it say? So in general, the collection of G functions over K, let's say. Then there's a constant such that the elements of the following set. So this is a set of algebraic numbers for which the Fi satisfy what's called a non-trivial global relation of degree D. So I have to explain what sort of these things mean in a minute, but at X. Right. So, okay, we all, there's some notion of a relation, and the set of points, X and Q bar, where these G functions satisfy such a relation, have bounded height. And in fact, the bound is logarithmic height to the C. And
Why is the
what
is the notion edge of your X? Ah, okay.
Sorry, I had a moment.
No. I'm just looking at
and just one point, because I think this is salient towards maybe some advances that other people are responsible for. This constant is effective. So that might be useful at some point. And in fact, Martin has even applied it to unlikely intersections in the Abelian varieties to do some new proofs of effective unlikely intersections. Okay, so what is a global relation? So a global relation is simply a polynomial, homogeneous, P over K, such that if you plug into this polynomial that has the right number of variables, the values of your G function at X, then this is always equal to 0 in the completion KV, as long as, well, so it has to make sense, right? So as long as all V such that the absolute value of X is bounded by, well, let me put the notice of the v-adic radius of convergence, the VI. And in fact, you don't have to do slightly better. You look at places where the v-adic absolute value of x is bounded by 1 and all the radii convergence of the G functions, right? Those are the places that you have to take care of. And that was why has relevance to this thing here. So that's what a global relation is. So it's quite stringent, right? Because somehow you have some sort of arbitrary number of places, right? You don't a priori know too much. And you have to sort of construct a relation that works at all of them. And somehow is that, you can't just go crazy and have a huge degree equation because that's going to wreck the bounds coming in. Non-triviality is easier to state, so I won't actually even write it down, but let me say it in words. Of course, how a series can just satisfy relations over, say, k round brackets x, right? That could just be algebraic relations between the power series. If you take one of those relations and specialize at some x, it can't possibly tell you anything important about the arithmetic of that little x. Okay, so non-trivial means not a relation that came from a functional relation between the G functions.
Would allow capital P to be defined over after.
Yes, I could make this bigger and nothing too bad would go wrong. Okay, so what's the idea? So you take a point on your base and you say, okay, the fiber has, additional cycles. A la Hodge theory, a la the, other talks of the workshop. And then it's almost tautological that the periods of that fiber satisfy some additional Q-bar relations. Right, we've sort of seen these things that somehow, the period matrix lands in the amongst the take groups. So, if that goes down, i.e. this sort of thing happens, then this gives you a relation. Then you kind of have to fiddle around and hope for the best that you can pass this to the G functions, right? Because there something a bit funky happened. I introduced some transcendental numbers and it's not so clear how well I'm going to succeed. But if that works, then at least, let's say over an Archimedean place, I can just take all the relations I get for all those Archimedean places and multiply them all together and get a relation that's like pretty well related to the number of Archimedean places, which is just this field of definition. So that's great. Right? That's exactly the kind of thing that we wanted due to Pila's and Massey-Fistol's. But somehow a subtler issue is I also need relations at the finite places. So I need to somehow control how many there are and what are the degrees of the relations appearing there. And this has always been, I think, often a slightly more difficult problem. And so in early iterations of this method, one would maybe just restrict to fibers where finite places don't show up in this sort of V-adic proximity, and then things are a little easier. Okay, so we want to apply this to a very simple setting. So in our setting, we just have elliptic schemes. So, you know, having a curve or a subvariety in y1 to the n is tantamount to the same thing as just having n elliptic schemes over a base curve C. I mean, okay, maybe I have finite changes and so on, but these are sort of one and the same thing. So we're going to run the G function game with n equals 2. And we're going to give ourselves a base point. And we're going to suppose that there's an isogeny at this base point between the two families at S0. Supposed to mean isogeny. So that's somehow the B that we had in the beginning of the strategy. It's some fixed base point with an isogeny. And then we're going to go trying to control the other S's. I'll enlarge K if necessary to make S K rational, where there's also an isogeny between the families at that point. So we apply the G function method somehow to these two families. Right, so this is a little, apologies, because this is kind of a bit of a repeat now. But so we need a basis again, say BI, omega I, eta I, say, for the Durham cohomology algebraically. Let's call that WI again. Then we have to pick a place and choose a horizontal basis. For so WI and nabla over some delta. Delta has to be chosen, and in particular, I'll choose it so that if V is a finite place, I'll choose it so that whenever a point lands inside this disk, the fibers have the same reduction as they do at S0. It's like residues. So omega I will be the base, the matrix again. BI with respect to I tilde. And then I use the isogeny at S to construct a relation between the corresponding G functions cooked up in exactly the same way. So if you this is just linear algebra. So no, F induces a map from W2 at S to W1 at S, right? So pull back on the Durham cohomology. And then if you check, well, I can sort of do two things, right? I can either work with respect to the VI basis and then do the isogeny, or I can sort of work with respect to the VI tilde basis and then do the isogeny and change it back, sort of thing. So if you sort of put those things down in the right order, then you just get a simple matrix relation, which is that A omega 1 has to be equal to omega 2. So unraveling, that is A F1 omega 1 S0 minus 1 equals F2 omega 2 S0 minus 1 times N. And then you get lucky because these matrices are problematic. They're transcendental, right? They're the periods of an elliptic curve without complex multiplication. But what you can do is take traces. And you can make those go away and get that the trace of N is equal to the trace F2 minus 1 A. So that looks very promising. The only problem is N, remember, was cooked up analytically, right? You chose a place V of the number field, you chose this horizontal basis, you then wrote this isogeny with respect to that one. It sort of heavily seems to depend on the place V. So this is not yet a Q-bar relation between the G functions of the families. But, it's not so bad. I mean, so turns out, okay, I think everyone in this room might sort of handle this problem ever so slightly differently, but let me just say, because I'd like to get to my point, let me just say this in words. It's quite easy to show, if it's an infinite place, it's quite easy to show this is actually in Q. If it's a place of good reduction, you can kind of copy that argument using the crystalline cohomology, show that that trace is also in Q. If it's a place of bad reduction, again, probably the more sophisticated people would use log crystalline cohomology or whatever. But actually, if you just use the tape uniformization, right, so let me just sketch this one. So V is a bad place. In that case, you have this uniformization by GM over this small enough disk. And the isogeny F lifts to the torus. The torus doesn't have many isogenies, just Q power laps. And then if you take this relation, you sort of lift it upstairs to what's happening on the Dram cohomology of the torus, and you get something like A omega 1 times Z over Z equals Q omega 2 dz over Z. Zero. So hey presto, the M goes away, and again you have something less than Q. So what you can do is then take all the relations that you get. I must stress, as far as I can tell, this number does vary as the place moves. It'd be amazing if it didn't. And multiply them together. And that's a global relation, and it's easy to see that it's not trivial, right? The trivial relations are incredibly easy to study in this kind of basic problem. But it's just a product over all the places that appear. Okay, so the degree is exploding with the number of places. Okay, so that's the last thing to deal with. I think Jacob was joking about having a course on board management. Did you say that in the code? I definitely really, I'm like the worst. I'm really sorry for my comfort zone. Anyway, so we go back to V in Y1Q. So now, if you like, we have 3 families. And I guess to sort of keep the flow of the explanation going, I sort of think of this as sort of 2 pairs, right? This one and then this one. Like, so I can sort of defunction game with the 2 pairs. So as I said, theorem 1 doesn't really use the full host of ideas. So here, what we do is eventually just project down to those first 2 factors. And then remember, so up here you had S0, which was let's say like of this form. It was in the boundary, but the first two coordinates are not in the boundary, like they're isogenous points. So you have this point xy on this projection, xy isogenous. But then if you look at a finite place, if your point lands in the disk, remember that we have to have that the third fiber reduces to the fiber S0, which will be GM because of this one. But then all the EIS's are isogenous, and so V has to be a place of bad reduction. Okay, so somehow there, the trouble's gone away, because then the number of places is just the number of bad places of bad reduction of some fixed elliptic curve, which is just some constant. And then the Archimedean places give you something. Something like this, right? The number of places of the line of infinity. And then very lastly, if you work with all three coordinates, you can't have this trick, right? This was a trick that we just employed towards the end. But I mean, it was George that first noticed that actually when you're in an ordinary place, you can work a little bit harder and use all three families to show that you can get one relation that works for any ordinary place. Okay, somehow in an ordinary place, it's sort of place independent, and that's simply because the endomorphism ring of an ordinary elliptic curve is commutative, and the property of matrices commuting is an algebraic relation that doesn't depend on anything else. So there you have independence, but of course the supersingular primes still cause the degree to grow and grow and grow, and that's why we have the thing that's now been erased that is sort of artificially imposed. It's somehow the limitation of the method. Anyway, I'm out. Sorry.
Okay, thank you, Chris. Any questions? Could you say a few words about why the conditional supersingular prime helps you out, like if you want to reduce radius?
Oh, I mean, essentially all I'm saying is that if you remember, like the number of them, is like is constrained like this, and so this, whatever this number is, will then show up in the number of places, and therefore the bound on the height. But as long as it's not too big, if you remember at the beginning, I said you can have some cheeky factors in the height bound, and isogeny estimates are still strong enough to, because basically what happens with isogeny estimates is like you have some with n over here, and you have height and Galois here, and if height happened to have some, n to the 1 over 10 here, it would be okay. You could get rid of them and you could still be all right.
So yes, I come back to this supersingular exponent. So you gave a definition, application of the theorem, but where does this notion come to show up in the proof as an assumption, a conclusion? So
how is it
you gave
used?
a definition as then in the proof?
It's not seen.
Mentioned.
Yes, sorry, that was similar to mine. Yes, sorry. So basically what I'm saying is I'm powerless to just, because you understand really well, just create a relation at each supersingular place. Maybe it's degree 2 or something like this. And then my final relation will just be the product of them. And then I get some height bound that's going to have that number of places involved. And what I'm saying is, it's okay that that number comes into the picture, as long as it's not too big that it kills the other side of the isogeny estimates.
That is by assumption or?
No, it's as stated is as used.
Okay, no further questions, then that's.